All right. If you look at the board here, just make sure that we're clear as to what's going to be on the quiz, as well as what is expected in terms of what I give you and what's you have to memorize. First, calculators are allowed. Okay. Next, summation rules and limit definition will be provided. With formula will be provided. So I'll give you a formula sheet with those summation rules, area formula. Okay. But the next ones we have to make sure we memorize. So make sure you know how to apply power rule. Memorize your trig integral rule. We talked about how we're not necessarily memorizing them, right? We're just deriving them from the 6 trig derivative rule. So I would write them out at the top of the page, and then just know that your integral rules, you're starting on the right side of your rule and moving to the left. And so we'll practice that. And then memorize areas of rectangles and trapezoids for your Riemann sums and trapezoid approximation. All right, so let's start off with number one. Number one, it looks like, oh, I got to do all this messy summation rules or summation rules, but there's no need for them because what do you notice about this that makes it not too bad? Yeah, there's only how many terms are we going to add together? There's 3, right? It's not like we're going from 1 to 100 where we have to use summation rules to try to break it down. So we just do this by hand, right? So we're going to insert I first with what value? 2, right? So we plug all that in, and then we do what operation do we do after that? Then we do what? Addition. Yep. So summation notation means we're just going to add. It also says find the sum. So plus, and then what's the next term you plug in? 3. Yep. You're always going to keep going up by 1. Plug that in. That will get you your sum for your second index value. And then what's after 3? 4. So plug 4 in for I. And you stop there. And then we stop. Yep. So the 4 doesn't mean, oh, I got to do 4 terms. 4 means that's the last I value you plug into your expression. Okay, try that. See if our answers to match. You can use your calculator if you like.
I don't know if do like some fish and stuff like I'm not like boiling it out.
Because there's only a few terms here. We don't have to worry about cleaning all that up and using summation rules. I'm just going to plug in. And just
If it's like less than like.
right. Yeah. And then really the summation rules will only come into play when it's like an area problem like this where Yeah, like this, where you have to, well, actually, what exact area, yeah. Any questions? All right, let's look at number 2. Number 2 says now we're going backward. Now we're trying to create some summation rule that will be a condensed version of these 4 terms that we see in front of us. So the way that we can start this off is, you have to build your summation rule. Typically, I like to start with 1. That's usually where it's going to be easier to start with. Sometimes you can start at 0 if it makes it easier, but I would always test 1 first. And if 1 feels like it's hard to create, then maybe start at 0. Okay, so we want to be able to plug 1 into some expression that will produce this term. So we hope that if I plug I equals 1 into this expression, I can get this one. And then when I equals 2 gets inserted into expression, I'll get this. I equals 3 will produce this, and I equals 4 will produce this. So I like to start off by just go ahead and copying down the parts that are not changing, because if it's not changing, then we know it's going to show up in every term. And the parts that are changing, we can involve the variable I to adjust for that changing aspect. So what parts do you see that's not changing in the expression? Yeah, the cube root, the division sign, the minus sign, the 5. So can you think of something that involves I that if I have a rule here, if I plug 1 into that rule, I can get 2 when I is 1, and then 4 when I is 2, 6 when I is 3, and 8 when I is 4. 2I. Now, whatever you create, always test it out, right? You should be able to convince yourself that, okay, this is definitely correct because it works, right? So you never have to guess and not be sure. I would always write it out, but always test it out, because if it's not correct, you can always go back and adjust it, right? But let's test this out here. So if I plug 1 in for I, 2 times 1 is 2, 2 times 1 is 2, so that proves the first term. I equals 2, I get 4 and 4. I equals 3, 2 times 3 is 6, 6 and 6. I is 4, 2 times 4 is 8, 8 and 8.
You put a 4 in top of this.
That's right. So this actually is not dot, dot, dot. If it was dot, 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 then I would go to infinity. But this one, there's only 4 terms here. So if I plug 4 in for I, that's going to be the last term that I need to get. Yeah. Not necessarily. Yeah. So they may follow a different pattern, and we may have to create a pattern for each term. So let me show you some of the common ones that could show up. Some common patterns could be just a matter of multiplying by a coefficient to create that pattern. It could be 2i or 3i. It could be something involving exponent, like I squared. Maybe it goes from 1 to 4 to 9. If that's the case, I squared could be something that you could test. Sometimes I cubed. Sometimes it could be like 2 to the I or 3 to the I. It's just something involving, exponents and multiplication. Those are usually the most common ones. And if you can kind of have those rules in your toolbox, you can kind of just test them out and eventually get the one that will fit. But you know that anytime that there's something is changing, I has to be involved, because that's going to allow for that changing portion of your expression.
So these problems are just recognizing patterns.
Yeah, recognizing patterns. Yep, that's basically it. Yeah. Recognizing patterns and maybe doing a little bit of trial and error. And by the end, you should feel confident that, whatever you get is correct, because if I can test it out and get every term showing, then that kind of takes the guesswork portion out of it. I mean, you are guessing, but you're also confirming that you have it correct.
I think one could be one of those.
Yeah, something along these patterns. either multiplication or something involving an exponent or exponential. Okay, number three is middle rectangle approximation. So we have to create our subintervals, build our subintervals, and then find the midpoint, and then plug the midpoint into the function. Okay, so first we need to find the width, and the width formula will be given to you. It's just b minus a over n. Right, what's my a, b, and my n value? Mm-hmm. 6 minus 1 divided by 3. Yeah, 3 middle rectangle. Okay, so that's our width. Our width is 5/3. Let's just do an abbreviated x-axis so that we can kind of move along our subintervals. We're going to start at what? 1. And we're going to keep adding what? 5/3 until we hopefully get to 6. Okay. So 1 plus 5/3, that's the same thing as 3 over 3 plus 5 over 3. 8/3. 8/3 plus 5 over 3. 13. Okay. Plus 5/3. Yeah, so I get 18/3, which is the same thing as 6, right? So let's go wait to check that you're adding correctly and you got the correct width, because if I can start at the end, get the number of intervals that I want and arrive at my right endpoint, I know that I did my intervals correctly. Now I could just use these x values and plug into the function if I'm asking for right-handed rectangles or left-handed rectangles, but it's asking for middle rectangles. So I need to figure out the midpoint and then plug into the function to get the height. So how can I find the midpoint between 1 and 8/3? Yeah, add and divide by 2, right? Or how about this? Add and multiply by 1/2. So 1/2 of dividing by 2, same thing as 1/2. I mean, I guess it doesn't really matter since you're using your calculator. You can do it, but without a calculator, I feel it's easier to multiply by 1/2 instead of dividing by 1/2. So if I do 1/2, 1 is same thing as 3 over 3, right? So if I do 3/3 plus 8/3, I get 11/3. 11/3 times 1/2 is what? 11 over 6. So 11/6 is the midpoint that I'm going to use to plug in to get my height. Okay, let's find the other midpoints here. What's the midpoint of between 8/3 and 13/3? You can reduce that if you want, or you can leave it as 21 over 6. Yeah, either is fine. You're using your calculator to do everything. Okay. What's the midpoint between 13/3 and 6? Okay, so area is width times height. We're going to do area 3 times because we want 3 rectangles. Okay, what's the width of my first rectangle? we found that, right? 5/3, that's going to be the width for all the rectangles, but. Okay. Okay, what can I do to represent the height? I'm not going to find the height just yet. I just want to do it in the function notation, so I know that I have it correct. What will represent the height of my first rectangle? Yeah, f of 11/6, right? Plug 11/6 into the function. That'll give me my height. Just indicating what I plan to do, and then we can do the calculator portion at the end. Width times height, and we repeat the process for the other two rectangles. Okay, and now it's just a matter of busy work in your calculator, right? So hopefully now it gets more straightforward. You're just plugging into the function to get the height and then adding up your individual areas. I would say 3 decimal places would be good for your approximation. That's also the common theme for a common standard for AP exams, where if you're ever approximating decimals, you're going to do it to 3 decimal places. Okay, any questions here? Okay, let's do a couple of Riemann sums. This one is going to be similar to what you guys did yesterday at the end of class. I just didn't, I should have, but I didn't I didn't copy the table out multiple times. That will make it easier for you to draw your brackets. So that I only gave you one table for each of the for these 4 problems. So you may have to kind of lightly build your subintervals or erase to get to the next one, but hopefully that's not too much trouble. So yeah, go ahead and try A through D, and then I will walk through. We can check our answers. So pay attention to your subintervals. Pay attention to the formula you're going to use. Rectangles is always width times height. The trapezoid is going to be 1/2 width times height 1 plus height 2. Okay, so try those. Hopefully, I mean, based off what I saw yesterday, it seems like we should be pretty good with these. I'd say yes, subtract, yes. Left hand, right hand, that side of or something. That's nice. Oh, but let me give you the key. You have it. Oh, yeah, proper facility. Make sure we memorize this by Friday. And has that rectangle, oh, sorry, triangle formula about it, like 1/2 width times height, but then height one plus height two. You like the Western's. Yeah, so you get to build your sub intervals here. So here, I'll go from 0 to 4, 4 to 6, 6 to 7, and let's subtract those numbers. So 4 minus 0 is 4, 6 minus 4 is 2, 7 minus 6 is 1. So those are your width, your height. You're gonna open the second row. There's about 3 left hand, so 1. First of all, that's not gonna let wide out of each sub.
So it's like the first value minus six value. Like when there's.
Yeah, always go, yeah, do right minus left.
Okay.
To get the width. Yeah, yeah, but you always subtract it to get the width. All right, let me put the answers up, see how you guys did. Any questions? Everybody comfortable with rectangles and trapezoids? Okay, let's go to area of or finding the area using limit definition. So let's go to page 38. Okay, so this is where we have to involve area formula, summation notation, limit as n approach to infinity. So I want to show you real quick what your formula sheet will look like. It'll be what you see on page 34. Okay, so this is what your formula sheet will look like. It'll have all the summation formulas. Sorry, I'm not going to give you the trapezoid area. Okay, you're gonna have to memorize that, but I'll give you area definition. And I'll give you the width formula. Okay, right now I'm just going to put on the board here as we walk through our problem. Okay, so it says given the region bounded by 6 minus x squared, the x-axis, x equals -1 and x equals 2, use the limit definition to find the exact area of the region. Okay, so we're going to start off by finding the width. Okay, now here we're not going to have an n value, right? It's not like, oh, n is 3 or n is 5. We want to leave n as n because we want to push the number of rectangles out to infinity. So we're not going to replace n with a number. Okay, so let's build the width first. Width is b minus a over n. What's my width going to be? Yeah, 2 minus -1 over n. Okay, let's build our width. Sorry, we have our width. Let's build our height in function notation. F of what? -1 plus 3 over n I. Good. So remember how the previous problem were midpoint rectangles were we had to actually build our own subinterval. We kept adding 5/3, and then we found the midpoint. And so here it's doing all that for us. It's creating that engine that will find the next subinterval for us. We don't have to do it. We just have to be able to plug into the formula. Now we have our width and height, but this height is still not in expression form. We got to get it out of function notation. So we know we have to involve this g of x here. So sorry, I call this f, but I could just as easily call this g if I wanted to, just to make it match that variable. So let's build our g function first, or let's rewrite our g function first so that we know where the argument goes. Now, everywhere you see an x, we're going to spend the time to rewrite your expression so that you have a reserved spot for that argument. Now, that -1 plus 3 over n, you're going to know exactly where it goes because it's going to go in the set of parentheses that you created from your function. Right, so now we can start inserting into our formula and then start building this out. Now, most of our efforts is going to be with the height component, right? There's quite a few things we got to do. We got to FOIL this out. We got to distribute the -1 through. Then we got to combine the like terms with the 6. And once all the like terms is now nice and clean, then we can multiply the 3 over n through. And then we can start worrying about their summation rules. And then we can do a limit as an approach to infinity.
Is that a G?
Yeah, that's a G there. I just want to just indicate that, we're using G function here. But if you didn't do that on the quiz, that's fine. I'll probably leave it. I'll probably give that as an F so that it doesn't. Okay, so let's see if we can take each of the steps here. Once you have your height component all cleaned up, you should be down to 3 terms. And then you can involve the width, multiply the width through. And once the width is through, then count the number of terms. And that's going to be how many summation rules we're going to have to involve. There's going to be a summation 1, a summation I, and summation I squared after we pull the coefficient and the n variable out in front. Any questions so far? Yeah.
Why wouldn't you multiply the 6 all the way out?
Oh, you mean right here?
No, the next one, like,
This one
it's
here.
multiplying.
It's 6 minus this expression.
Oh,
So I'm going to distribute the -1 through first. And then once I multiply that through, multiply the -1 through, it's 6 minus 1, so 6 minus 1 is 5. It's not 6 times.
Oh.
If it was 6 times, then I would distribute through, but it's 6 minus parentheses. Okay, so once we identify that there's 3 summations that we want to involve, we're going to go ahead and pull the coefficients out in front so I can isolate the parts that it's going to, where the rule is going to apply. So summation 1, I have a rule for that. Summation I have a rule for that. Summation I squared. And we know that from each fraction, we're just going to find the matching pair of highest degree, and that's all we care about. And we just care about the coefficients attached to them. So that's going to save a little bit of time here. All this mess is multiply the 27, the n, 2n to get that first term. And that's all you need to get the fractional value from that third fraction. Yeah.
we did the formulas for like the I squared.
Yeah. So if you turn to page 34, those are the rules I'm going to give you.
I do in like the second section in the middle.
Went from that 9i squared on the lower part of the left. So on the lower part.
Right here.
Yeah, how'd you go from plus 9i squared over n squared to minus 9i squared?
So I distribute a negative one through to get rid of the parentheses. So that's your distribute negative through, I can drop the parentheses and, so it's actually 6 minus 1 plus this minus this. Okay. And then the 6 minus 1 is 5. I just skip a step. Okay, any questions here? Okay, the things that we did not finish on the worksheet is just power rule, the integral rules for trig, and then what we did yesterday with general solution and specific solution. So I'm going to adjust the homework a bit. The homework on the calendar says for the textbook problems, we'll scratch that. I just want you guys to finish worksheet 1, and I'm going to check that for homework for tomorrow. Okay, I'll send out a reminder this afternoon that I'm changing the homework assignment. And I'll send out a link to worksheet 1 so you can check your answers. Okay. And then tomorrow we'll go over worksheet 1, make sure you're good. We'll do worksheet 2 in class. And then Friday morning, I'll have help session for worksheet 3. All right, come in above. Well, this n squared. Yeah, n squared and this n squared, that's 2n squared. This 18 times n plus n squared, 18 squared. Yeah, that's 18 squared, 18n squared plus 18n. I dropped the 18n, but 18n is not gonna matter between these two.